Hi, I'm David, and I'm presenting my work for the compilers class. So I'm just going to get to the screen sharing right now. And so I'm not going to go too in depth. So I'm just going to present about all the stuff I did, but I'm not going to go too in depth into all the algorithms because then that would take. I tried that, and that was taking a bit too long. So first, I'm just going to briefly go over stuff just so you can see, like, there's the passes first, the initial pass of the initial implementation, like the basic part of the compiler. That's the uniquify, and then it's the flatten. Uniquify, just making all the variable names unique. So the way I did that was add this num unique vars static int set first at 0. The problem with this is that obviously, like, you wouldn't want to uniquify programs in a row and then flatten programs in a row because you'd want to uniquify and flatten in the same pass. So because otherwise the num unique vars variable would be kind of it still might work. No, actually, I wouldn't, because it generates the new labels for the flatten, for the return, or the return values of the R0 expressions based on this num unique vars. So then it wouldn't. I guess I didn't have to do it that way, but it would be, because I could have just counted the variables. But this way seems simpler. I guess maybe it's not actually the best way to do it, but yeah. So that's kind of a limitation, but it's not really a big limitation because generally you would want to compile the whole program instead of just like compiling pieces and then compiling pieces of each one. If you have a list of programs and then compiling the next one, so you can see here, like, I'm just going over the let expression for the uniquify. So first you would have the variable, then you would have the value that the expression that you would assign to the variable, and you would have the body expression which you would return. So first, you get so for the uniquify, you would get the var name list. So then you get the name from the original variable name, and then you get the original variable name, and then you add this num unique vars plus plus. So you're making new value for num unique vars and making like a unique value for the new variable name. And then so then you're just making this new let but by uniquifying the expression for the XC, and then uniquifying the expression for the BE. So everything else is, like, pretty straightforward. And I wasn't going to get to the if stuff yet, but I was going to get to that after I get to the register allocation. So as I wrote here, that was what I just talked about. That I was relying on the static value, which maybe wasn't the best way of doing it, but it made the most sense for me at the time, and it fits within the use cases that I'm doing for testing it. So then of course you get to the flatten, and flatten would just generate this. So it still uses the unique vars, and then you would just get this new, like, just append. 1 second, I just wanted to check that I was live. Okay, sorry. Then you just append this num unique vars to that, and for the read and for all the other stuff. And then of course there was the stuff that was described in the class for flattening it, like just to show an example. For add, you would get the flattened program that's the children of the A, like adding A and B, and then you get the flattened program that relies on the children of B, but like the B. So flatten A, flatten B. And so then you would just get, and then this is just saying flatten expression 1, flatten expression 2, which now I realize is maybe not the best variable names, but so then it's just, you add all the variables from that flattened program, and then add all the variables from that flattened, and then add all the statements. So then you're getting the value of what's in the flattened A and B expressions that you're adding together. So don't need to go over that right now. So that's all the other stuff that I did for the if. So then next part would be the select. So that would just go over, like here you can see it's just moving the value. So at C0 add, it's moving the value moving the value from that you get from A into this new variable X. Or this is that's just the assignment, because here it's just assuming that it's just saying that everything is assignment, or it's not saying that everything is assignment. What exactly is it saying? So it's just yeah, so it is saying because in the initial C1 thing, it's because this is just the initial C1 language, so it's saying all the statements are assignments except the returns, but I didn't have return as a statement, and I didn't implement it like that. Maybe that was the wrong decision, but I'll change that when the time comes. So yeah, so just assuming that everything is an assignment, so it's just getting the assignment, so it's putting the 0, it's putting the A for the add into this X that's assigned, and then it's adding that value. So then it's generating the new move and add instead of the C0 type stuff. So this I'm not gonna, one second. Yeah, so then I don't think I really need to like go over the code for the putting the stuff into the stack. It just like the assign pass for the initial pass, the compiler puts everything into the stack. So that I don't really need to go over. And I'll just quickly demonstrate some code output. So just to show the tests that I had. Yeah, so like that would just be adding 2 and 3. So you would get 5. And I have the interpreter that puts out 5 for R0, and then here this adds 3 and 7 and negatives it. And here, so I'll just show those two quickly, yeah, I just want to show those two quickly because those are some, yeah. So then, and then I guess I don't remember all. I know that this is supposed to, yes, but anyways, yeah, this was a. Well, I'll get to that in a second. So just to show that it prints out the code. So actually, I already have it up here. So just to show quickly. So here it's saying expected value is 5 because it's getting it from. So when I go to this output tests, it's getting it from the interpreter, expected value 5, and then so it just adds in like subtract 2 spaces, subtract 8 from RSP, and then just for 1 space, and then it's moving 2 into RSP, adding 3. I mean 2 into 0 RSP, adding 3 to 0 RSP, and it's printing that, putting that in RX, and then putting it in RDI so that because RDI is the function arguments, and it prints it. And then just to show the, I guess because it's hard to see. I guess going over the code is kind of hard to see what exactly it does, because it takes a while to walk through. But let me just show you. So yeah, this was the program for getting power. So in this case, power 2 to the power of 10. So it's up right here. So getting 2 to the power of 10. So as you can see, it has 3,073 lines of code. But if I copied in, like I don't really, I did copy and paste all of this, which would take a little while. And also I'd have to get rid of the numbers. But if I did copy and paste all this, like, which was the way I was using to test it before, it would work. But yeah, now there was the different part. a different way of implementing it, just showing the value directly, just running the command and showing the value directly, but I'll show that after I quickly go over the register allocation portion, because I implemented that after. So, second, there's the fast methods. So I don't want to go too in detail on the algorithms because I did, of course, implement all of these. But I mean, I was basing it off the lectures, so it's not like I didn't. It's not like, and then the book, so it's not like I didn't understand it, but I just don't. I remember the general ideas, but I don't remember the very specific details. So I'd have to think a bit more to get to go over the specific details concretely. But in general, so first gets the register allocation. So of course it first gets the live after set for each instruction. So as the live afters and live befores are used to compute the live afters. So so like here, because when you're adding A and B, A is being read from, but B is being written to and read from. So then you would add A just to the read set and B just to the write and read set. Then for the first instruction, for the last instruction, because this is going backwards, you would just set this last live before is set to the read set of that last instruction. So that's just simple. And then the rest of this here, you would just get the live set from you get the live after set first from the live befores, and then there's some more stuff like removing the write set, and then removing the write set from the live befores. That's all. I think that's all you do. So then you get the live after set. So here, like I said here, so it's you remove and then you union it with the read set. So you so where do I have unioning it with the read set? I have union with the read set I have here. So it's first remove write set, then union the read set. Okay, so then that's how you get the live afters, and then build interference. Of course, build the interference graph from the live after list. So I have the adjacency map object that would have it's basically just it's partly a wrapper for so it's just a wrapper for map and has the API functions for adding to the map, and looking. So it just adds, it goes through and it follows the algorithm that's described in the book in class. So and then so here I want to print this out actually to demonstrate, just because that makes it more clear what I did. Or actually not not that. So then what you want to do is actually I don't think I want to print it out, but yeah, so coloring the graph, I guess this was probably the most interesting thing for me out of the stuff that I did. So I guess the idea was, you want to color something that's not colored based on the neighbor, like not the colors of the neighbors. Then like breaking the ties randomly. I'll show what I did for that. So I guess what I did for that was, so here it's just making a list of, it was just, so the uncolored It's just everything at first. I guess I don't remember exactly why I had a separate color map and saturation map, but it made the implementation easier, I think, or made more sense to me at the time. So this is just looping. So now here it goes through this main. So the saturation map, it's saying everything at first is saturated at 0, and then everything is colored -1. It's not colored. So here this is where it makes a list of the highest saturated vertices. So yeah, for X argon colored, so then it adds, so then it finds the highest saturation, and then so then it finds if it's equal to the highest saturation, then you add it to this high sat vertices list. So that's where you get the tie from, and then so then here this is where you break the tie. So you just get this random next int from the list of vertices, and then you just get that choice called color me, and then so yeah, and then you update, I think, you put the new color, which is just adding it's just max. So it's adding one more than the neighbors. So yeah, then it's also adding the saturation map value. Maybe, I think this was, I don't remember exactly why I implemented this way, but it works. So I think it's fine. So then this is where allocate the registers, which is based on the quote unquote colors that I had. So yeah, so I'm not going to go into too much detail on this because I wanted to get to the if part. But yeah, so as you can see, it goes reg names color if it's less than the reg names length, which is, I have the string array of the register names of the caller save register names. So then if it's less than that, then it puts it into the allocation map. It's more than that, then it puts it onto the stack. So then what I did, so then here before, for the initial pass, I had a I had a not modular at all assignment, which did the assignment to the register, it did assignment to the stack, then in the assign part. But here this is an assign modular. This is a modular version of that, so it gets map. So here is it gets this allocation pair, which is just so this describes how stuff is allocated. So you do the allocation in a different function. Like here I do it in the reg alloc. I do the same thing that I did for the initial pass, for the initial version of the compiler. And I could do that and pass it into here and it would still work. So now I'm going to get to the if part, which I only managed to complete up to the flattened pass. I want to complete that maybe by the end of this week or something. But so with that, oh, actually, yeah, I hadn't demonstrated. Let me demonstrate first. So I have the reg. So where is it? Just 1 second. Test. Oh, okay, it's right here. So what I had was I have this print x0. Actually, I want to talk about this even though I'm kind of a bit over time, because this not the print x0. There's the test, there's this direct compilation. So it's just running the process in the bash and then outputting. So I had some trouble here because it was printing the input. It was like printing the output, but then it was, if there were input prompts, it was printing that. But that was really stupid because that was just a problem that I had with the runtime, because I wasn't flushing after the printf. So that's why I was doing that. So once I put the flush after printf, it was, but yeah, anyways. So then what I did here was that I just So yeah, it has a separate threads for the error input and output, and it has basically this just termination. This termination thread process that just checks termination thread just checks if the process is terminated, and it just waits. Oh, because I didn't have to have separate threads because of this inherent I/O feature. I guess I'm not. This is kind of tangential, but this inherent I/O feature, which just passes all the input and output from the process to the Java. So then it just has this, and then so I don't have to do the output and stuff. I just have to check for the termination of the process. So it just says join if it's terminated. So just to demonstrate that on the tests that I have. Second, so there was this. So I have run tests reg alloc. That's this. So here, that was just adding 3 and 2, and it's 5, and this is adding 3 and 7 and negating it, so it's just -10. And yeah, so it's just running, it's compiling the stuff that you could see the code earlier, and then it's just running it. So you don't see it, but it's still working. I think this just adds 6. Yeah, so it adds 6, and then when I add 6 to the value, so then when I put in 10 here, it's going to be 17, or I mean 16. I meant. So then this is that was a different thing. So then this was compiling. So that was compiling the 1020 10 2 to the 10th program. You can't see it here running, but it is like in the assembly. It compiles the assembly and it runs it. So yeah, I'll just take a few minutes, or yeah, so I haven't completed that much stuff from the if yet, but I did complete up to the flatten pass. So I'm gonna show that. So so what I have so far, so Uniquify does get this if, but that's the same. So I guess what's interesting here is there's the flatten. So flatten. So when I get to the flatten if, so then I make this list of the if statements and list of the else statements. And so I guess what I did here that I kind of felt good about was, because I guess maybe this was kind of foolish, but I didn't want to implement, like, I didn't want to make a recursive flatten function just for the if, even though maybe that was a better decision. Actually, no, I did. It is a recursive flatten function. Never mind. That was for the, but anyways, I was thinking about the interpreter. Anyways, so here I have the optimization. So if it's checking if the condition is a literal Boolean, it only needs to compile either the if or the else branch. That's why this is here. But otherwise it just gets the condition and the statement list, and then it makes the new comparison. So then it adds the statements from the if. So anyways, what I wanted to show was in the interpreter. So the interpreter, I didn't want to make like a new recursive interpreter. So what I did for that part was I have it. So if so it has the flag. So if the condition is true, then so you have the current list of statements in the C0 program, but then it adds the statements from, if it's true, you add all the statements from the if. So that's if it's true. You add all the statements from the if. So this is just using the Java iterator. So it adds all the statements from the if branch, and then it goes back to where you were in the program, which is right after the if. And then so the else, it does the same thing. I like maybe that it doesn't. It's not really like an optimization. I just wanted to do it this way. Anyways, I just wanted to demonstrate this with one of the programs that I had because, so one of the programs that I had, so that is here. So the idea here is you enter a number and it checks if the number, so if the number is between 40 and 20, you return 1. If the number is so if it's between 40 and 20, return 1. It's a nested if, so if it's between 40 and 20, return 1. If it's less than 40, but greater than, if it's less than 40 and less than 20, then you return 2. And if it's greater than 40, then you return 3. And you put it into this y variable. So I just want to demonstrate that because I feel like there are other test cases that I have for the if part, but that's reasonably complicated. Not too complicated. It's still simple, but it just demonstrates multiple features. So that's why I wanted to show that. So I have that in test R2 flatten. So there's the R2 interpreter looks at it first, and it gets that value, and then the C1 interpreter looks at it after the flatten. So just to demonstrate it with a few different test cases. So if I say 31, and then for the R2 interpreter it says 1. For after it does the flatten, it also says 1. And then if I say -1, that should give 2. Then for the R2 interpreter, for the C interpreter, after it's flattened, if it's less than 20, then it should also give 2. And then it will be the same, just to show that it will be the same for the R, for if I enter something. So if I enter something greater than 40, it would return 3. So if I enter something else greater than 40, it returns 3. So yeah, that's all I wanted to talk about. I could go into, because I could have gone more in depth, but I did a lot, so I just wanted to cover what I was most interested in. I guess just some issues with how I had implemented it. I think I was kind of afraid of throwing away code, which is maybe that was kind of a big mistake, because that kind of made me intimidated to re-implement stuff. So, and also because I had all these tests and I wanted to make sure that which was maybe foolish. I just wanted to make sure that these tests worked for the presentation. I'm not using most of the tests, and I already know that they worked before, but maybe I should just keep. But yeah, so I just want. I don't have to have all the tests work, so maybe I can just, if I just re-implement it, and that for the register allocation, I hadn't tested it all before. I had implemented all of it, and then but instead of testing each individual part, like the building the interference, building the live after, which I did test, but then I didn't test the building into interference graph and the color graph before trying to allocate. So I think I should have tested those individually first. So that concludes my presentation. So thank you for listening. Sorry if that was overly long. Adios.